Welcome to Why Rocks, a BYU Department of Geological Sciences podcast. We are excited to have with us today Dr. Landon Burgener. And Dr. Burgener, how long have you been at BYU?
This is just my second semester.
Second semester. Why are we putting him in the podcast? I have no idea. I mean, we need somebody with some experience. Tell us, what is one of the most interesting things about you? What's something that our listening audience would just be fascinated by?
Oh my gosh, I don't even know. I was expecting all these science questions.
We'll get to the science questions, but we want to find out that you're a real person first.
Well, this isn't super impressive because Janie...
Okay, you never start off that way. And yes, we were going to go here anyway, so tell them.
Because Janie is in the department, but I've been to 5 of the 7 continents.
Yeah.
So I got to get Africa and Asia under my belt.
Very nice, very nice. While we're talking about continents, one of the 7 that you've been to, we've actually both been to.
That's true.
Same research project. Tell our listeners about your experiences in Antarctica.
So I went to Antarctica in summer of, the winter here.
Yeah.
The Northern Hemisphere winter 2010. 10. Thank you. I was blanking.
Because I went in 11.
You went in 11. That's right. And both of us were working on a project in West Antarctica, which is the smaller side of Antarctica, the smaller of the 2 ice sheets in Antarctica. We were collecting fairly shallow ice cores from the surface of the ice sheet, and yeah, it was an awesome experience. Antarctica is an amazing place to go. You step out of the plane onto the ice sheet, and it's big, it's flat, it's white, and
bright.
Very bright, that's true. And then
24 hours a day.
It wears off after, the excitement wears off very quickly because it's flat and white and bright. And
then you go to sleep, and you wake up and you go, oh, that was a great night's sleep, but it's been light the whole time, and you realize I've only been in my tent for 2.5 hours.
Yeah. Your
All
body
right.
has to adjust to it.
What is your area of expertise? What's your specialty?
So I guess I call myself a paleoclimatologist,
okay,
which is a fancy word for somebody who studies ancient climates.
How ancient?
So it can be, that depends on the researcher. My work is mostly focused on greenhouse periods, so times in the Earth's history when the climate was warmer than it is now. Specifically, I've looked at the Cretaceous period.
Lots of increased temperatures during the Cretaceous.
Yep. Very warm period. So it's kind of famous as the last period of the Mesozoic. So it saw kind of the biggest expansion of the dinosaurs and then ended with their extinction. And so I've been very interested in understanding the climate of that time period and how the Earth's climate system operates when we have really high atmospheric carbon dioxide concentrations.
What are your tools? What do you go out and look for?
So I specifically look at fossilized soils. That's kind of what I'm
That sounds fascinating.
No, it doesn't.
I was being sarcastic.
So we call them paleosols, and you really can preserve a soil in the geologic record just like you can fossilize and preserve an organism. And kind of my interest is looking at mineral accumulations in the soil because the chemical composition of those minerals can tell us about temperature and precipitation conditions while that soil was forming. So we can reconstruct environmental conditions from millions and millions of years ago.
How do you go about finding a paleosoil?
So they oftentimes you see them at the surface of the Earth as kind of badlands terrain. So they're these kind of low sloped, devegetated hills. They kind of look like they're just kind of slumping down.
Like the Badlands of North Dakota.
Yeah, exactly.
Or anywhere on the Navajo Reservation.
Yep. And a lot of times they're marked by really bright, beautiful colors. You get these kind of variegated bands of red and purples separated by greens, and then kind of
like the Chinle Formation down in southern Utah.
Yeah, exactly. And so that's kind of like your clue that you're looking at a potential paleosol. Okay. And then when you get up closer, you're looking for things like fossilized root casts and things like that tell you that there used to be vegetation colonizing the surface of that soil.
What causes all those really bright colors like we see if we go to petrified forest down by Page?
Oh yeah, so it's differences in how well drained the soil was when it was forming, and so a geologist would talk about differences in the redox conditions or the oxidation state of the soil.
Redox, you're going to have to break that down for just a second.
So basically, you're looking at whether so these soils a lot of times will contain iron-bearing minerals in them. And if the soil was a poorly drained soil, meaning it was pretty wet throughout the year, that iron in those minerals doesn't get exposed to oxygen, and so it doesn't rust. And so that would be considered a reducing environment. And typically your soils in a reducing environment are going to be kind of green and gray colors, drabber colors. In contrast, if you have a really well-drained soil, those soils get exposed to oxygen, those iron-bearing minerals will oxidize or rust, and you develop these really beautiful reds and browns and purple colors.
What pulled you into this? What made you think, oh, hey, I want to go study fossilized soil?
So when I started at BYU as an undergraduate,
Were you always a geology major?
No, I wasn't. In fact, when I got back from my mission, I started off as a political science major.
The mission in Peru where you didn't have to cook your own food.
It's true. The cheating mission, as you so kindly call it.
Okay, I'm just calling it like I see it.
So I thought I wanted to be a political science major. I took a bunch of classes. Didn't really love it.
Thought he wanted to be a political science major. I'm just trying to get my head around it.
And I was finishing up at BYU Idaho. Well, so finishing up my associate's degree, and I had one more science credit I needed to fill, or science class I needed to fill, and I just saw that there was a paleontology class being offered in the geology department up there, and I decided that'd be a fun class to take. And when I actually got into the class, I was the only non-major in the class, and all the other students were throwing around really cool words like depositional environment and clast size and all this stuff I didn't understand. And I kind of just fell in love with it. I'd already been planning on transferring down here to BYU when I finished up my associates. And so as soon as I got down here at the end of that semester, I declared geology as my major, started working at the Paleontology Museum. And from there, I just started taking classes and got interested in geochemistry and connected with a couple of different professors in the department.
Dr. Rupert
and Scott Ritter as well, who were doing paleoclimate kind of things, and it kind of just evolved from there.
So then you've got your bachelor's degree, you're working with Dr. Rupert on a master's degree, you've been to Antarctica, fossilized dirt. Where did that come from?
So I really liked the master's degree project I worked on. It was a really fun project. Working with Dr. Rupert was great, but by the end of it, I knew glaciology wasn't really what I was interested in pursuing. Part of that project had a geochemistry component. There was another grad student who Jessica Williams, who was looking at the oxygen and hydrogen isotopes in the ice cores that we collected. And that had seemed really fascinating to me. And as I got close to finishing up my master's, I was talking with Dr. Rupert about potential Ph.D. Programs that I could apply to and professors I could potentially work with. And she had gotten her Ph.D. at the University of Washington. And she knew a relatively new professor there, Dr. Kate Huntington, who was working on a new geochemistry tool called clumped isotopes, and that had really cool potential paleoclimate applications. And she suggested I get in touch with Kate and talk more to her. And I went out and visited the University of Washington, and it was an amazing program, beautiful campus, and kind of just went from there.
So then your PhD involved paleosols.
Yeah, so this was kind of in the early days of this new clumped isotope tool.
Now, explain really quickly to the people who are listening and myself, clumped isotope.
Okay, so stable isotopes is kind of a branch of geochemistry that has existed for a long time. And in geology, a lot of stable isotope work focuses on the stable oxygen and carbon isotopes of carbonates. which are minerals like, or rocks formed of minerals like calcite and dolomite. And so they form a variety of different rock types at the Earth's surface. And we can look at the stable isotope composition of those rocks to understand things about the formation processes and the environmental conditions that existed during that rock's formation. So what's an isotope? An isotope is a given element like oxygen, or in a given element like oxygen, you'll have some oxygen atoms that in their nucleus have 8 protons and 8 neutrons. The vast majority of oxygen atoms have 8
He got it right.
Neutrons. And but a small fraction of those oxygen atoms have a different number of neutrons in the nucleus. So for example, oxygen 18 is an oxygen atom whose nucleus has 8 protons and 10 neutrons. And it's a fairly rare oxygen isotope. Oxygen 16 is the most common oxygen isotope, and it has 8 protons and 8 neutrons in the nucleus. So that's what an isotope is. So what are clumped isotopes? Well, clumped isotopes instead of looking at a single atom, we're looking at a molecule. So the one that I look at in particular are carbonate molecules. So that's one carbon bonded to 3 oxygen atoms. And we're interested in knowing the abundance of carbonate molecules in our sample that have both a heavy carbon isotope and a heavy oxygen isotope. So that would be a oxygen 18 isotope bonded to a carbon 13 isotope.
Because carbon should only be a 12.
Yep. So because normally, the majority of carbon atoms are a mass of 12. So the reason we're interested in measuring these clumped isotopes is because the abundance of clumped isotopes is controlled by the temperature that the mineral formed at. So at lower temperatures, we'll tend to get more of these clumped molecules in our sample that have a carbon 12 or a carbon 13 and an oxygen 18 bonded together.
And since these are surface minerals that you're looking at, you're interpreting surface temperatures.
Yeah, so since I was looking at soils, or carbonates that form in soils, those are the carbonate formation temperature of the soil.
Okay, so how much warmer was it when T-Rex was romping around the planet?
So that's a great question. It kind of depends on where you were. We talk about like the average temperature difference. So comparing the Cretaceous to now, the average global temperature was about 12 degrees warmer than right now. So that's more than the difference between, now I should have come up with a good geographic example. It's much more than the difference between the average temperature of like Raleigh, North Carolina, and Boston, Massachusetts. So it's a big temperature swing. Now, depending on where you're at on the Earth, that temperature difference between now and the Cretaceous could be larger or smaller. So at the equator, temperature differences are typically smaller, maybe a couple of degrees. But at high latitudes, so close to the North or South Pole, those temperature differences can be up to 20, 25 degrees.
Wow, that much.
Yeah, so we tend to see an amplification of temperature differences at high latitudes.
So when the dinosaurs were here, equator would have been similar to today, but Utah would have been warmer.
Yeah, and so the equator still probably would have been
a few degrees.
A few degrees warmer. Yeah, that's what our current best evidence suggests. But yeah, the higher latitudes would have been significantly warmer. And that sets up really interesting questions about what were environments like at those high latitudes, because even though they were significantly warmer, they still would have experienced the same light conditions that high latitudes experience today, meaning 6 months of sunlight in the summer and 6 months of darkness in the winter. So there's still a lot of open questions about what environments and climate systems at those high latitudes would have really been like.
What instrumentation do you generally use to do all of these analyses?
So once we collect a sample out in the field from one of these paleosols, we bring it back to our lab and we powder it up. So we take our carbonate sample and grind it into a small
You don't. That's what you have graduate students
for. That's what I have. That's what I have graduate students
Just making sure.
And well, I guess first off, we have to carefully inspect the samples to make sure that they haven't been altered. And as geologists, we talk about diagenetic alteration. And the reason we want to screen out samples that have been altered is that the isotopic composition of those altered samples no longer reflects climate conditions. Instead,
when they were formed.
Instead, they reflect burial conditions. So they're controlled by how deeply was the rock buried, how long was it buried at a given depth, or was hot water circulating through the rock at certain times.
So the data would be erroneous if you used it.
Right. Yeah. I mean, you couldn't use it for paleoclimate information. You could use it to understand tectonic processes or burial histories of a basin, but it's no longer paleoclimate information. So, anyways, we screen those data out. We powder up the sample, and then the actual instrument we use is a machine called an isotope ratio mass spectrometer. And so
that sounds impressive.
It does. They're amazing instruments. They are incredibly fickle. They're difficult to keep running.
Incredibly expensive.
They're very expensive, but they allow us to make these really high precision measurements of the isotopic composition of whatever type of mineral or substance you're interested in.
And do we have that machine right here on campus?
So we have a conventional mass spectrometer that it has not been working for a few years, but we're in the process.
Sounds like a problem.
Yeah, we're in the process of getting it up and running. It's that particular instrument doesn't have the required precision to measure clumped isotopes. So once I get out in the field, like we said, I'm a pretty new professor. I don't even have one field season under my belt yet. But once I get out there and collect some samples, we'll probably do our conventional isotopic measurements in-house. And then when we identify samples that are a good target for clumped isotopes, we'll take those to an outside lab. There are more and more clumped isotope capable labs out there. University of Washington has a big one, University of Michigan, North Carolina State. So there's a variety of places we could take them to do those measurements.
Your focus, your target areas here in Utah would be Morrison Formation, other places?
So far, the Utah formations I've looked at have been a little bit later. So we've been looking at the Kuiperowitz Formation down in Grand Staircase Escalante.
More Cretaceous stuff.
Yeah, so that's about 75-ish million years ago.
Only 75.
Only 75.
Relatively recent.
And then the other one I've been working in recently is the Straight Cliffs Formation, which is a little bit older than that, around 95 million years ago. Also located in the same general area. This summer, I'm hoping to get out and sample the Weigh-In Formation, which is actually exposed up in southeast Idaho and Wyoming.
But first, the snow has to melt.
Yeah, first we'll be waiting a while, I think. But the Weigh-In Formation is equivalent to portions of the Cedar Mountain Formation, which we have here in Utah as well. Yeah.
So would Cedar Mountain be a potential target as well?
Definitely, and I should say I've done work in the Cedar Mountain as well. Yeah, so. Cedar Mountain's a really cool formation.
Yes, it is. And it has dinosaur bones in it.
It does, yes.
Does what you do have application to modern day, climate change, the stuff that we hear about on the news?
Yeah, that's a great question. So probably the most relevant application is that we're in this state of increasing temperatures in the world, and governments and organizations and societies want to plan for the future and understand, what steps do we need to take to prepare for and hopefully mitigate some of this environmental change that we're expecting to see. In order to do that, in order to plan for the future, they need predictions of where the climate's headed in the future. And we make those predictions using really complicated state-of-the-art computer models that simulate climate. These are called general circulation models, and they simulate global climate using our first principles understandings of physics and chemistry. We need a way to test those models. And these models have been tested extensively against modern climate. And we know that they do a really good job of predicting modern climate conditions. But there's really no way to test how accurate their predictions are of the future, where we'll have an increasingly warmer climate that may have different processes or slightly different behaviors to what we're used to. There's no way to test their predictions unless we can compare them to past warm periods in Earth's history. And so one of the questions I'm really interested in is understanding how can we use our data about Cretaceous climate or about early Cenozoic climate, which is another warm period in the Earth's history. How can we use those as test beds for evaluating the accuracy of these models? And that's been a goal of paleoclimate research for a long time, and the community's been making, I think, really cool strides in improving our ability to compare these climate models to past climate data. Hopefully the result is that we'll be able to improve the accuracy of these climate models and get better predictions of where we're headed in the future.
Do you see yourself going back to Antarctica?
I don't know.
I know a number of students in our department that hope you do.
Oh, really?
Because they want to go too.
So I don't think I'd go back to Antarctica to study ice, but there are some cool formations exposed both on the Antarctic Peninsula, rock formations exposed on the Antarctic Peninsula, in the Transantarctics, and I think also a few in the dry valleys. So there's Cretaceous-aged formations.
With dinosaurs.
Yeah, there are.
Cryolophosaurus lives there.
Yep. And then there's... Oh, sorry, you go for it.
Lived there.
There. It'd be a cold place.
Yes.
A cold place to live now. So, I don't know, maybe in the future. It's hard because working in Antarctica requires you to miss Thanksgiving, Christmas,
New Year's.
It's a long time to be away from
is.
the family. But it's a cool place to do research.
Yeah.
Would you ever go back?
I'd go back to McMurdo.
Yeah.
If I could take my wife with me.
I'm trying to convince my wife that she would like to go.
I would love to spend Thanksgiving in McMurdo with my wife and have Thanksgiving dinner at 153 and, go to the little concerts they have in the evening. C17. I mean, yeah, some of those songs you can download off of YouTube. I wouldn't mind going out to the deep ice for a day or two.
Yeah.
Bird camp or waste divide.
Yeah.
Someplace where there's infrastructure and a galley and bathrooms.
It would be cool to go see the South Pole Station.
But see, then again, you still have the infrastructure.
Even more than at like waste divide.
No, I was a bird.
Oh, you were a bird?
Yeah,
I didn't know
bird.
that.
Yeah.
Oh, cool.
So waste divide's a little more civilized than bird. Bird, they pack back up into boxes and bury in the snow every year.
Oh, geez.
Yeah. So it's just tense.
Yeah. So they didn't even have like a big galley or anything.
They did. So the galley at Bird was a Quonset-style tent that was probably, 75 feet long.
Yeah.
And just full of tables. And then the back end of it was where the snow melter and the chef. Because the food was incredible.
Isn't that crazy?
Yeah.
Like the U.S. Antarctica program was way more extensive than I expected.
The gentleman who cooked for us at Bird Camp on Christmas Eve, because we made it back to Bird from the ice on the 23rd of December. So the gentleman who cooked, it was New Year's. We were out on the ice on Christmas.
Yeah.
So the gentleman who cooked New Year's dinner was a chef from some upscale 5-star restaurant in New York City. And he comes down and cooks for a month and a half at Bird Station every winter and had been doing it for like 10 years.
That's so cool.
So dinner, I couldn't even tell you what we ate. I can't pronounce the names of the things.
I've tried to convince my wife that, I don't know if do you remember in McMurdo there were older couples that would drive the buses around?
Yes.
I've tried to convince my wife that would be a cool thing to do for one summer, but she seems
because
iffy.
It's summer, but it's still, on a good day, 32 degrees.
Yeah.
Fahrenheit. And on a bad day, you're confined to quarters and the wind chill's 40 below.
Yeah.
Yeah, no, it'd be cool. It'd be cool to be there when the icebreaker comes in.
Oh yeah,
and opens the channel, and then they unload the cargo ship, and we didn't. So, but when I left, there really weren't any penguins even because
I didn't see any either.
The shelf ice was still 5 miles wide, so the penguins aren't going to walk across that to see people.
It was one of those experiences where right when I got back home, I was like, never again. And then as
Oh,
it gets further and further in the past, I'm like, oh, maybe I could do it.
Yeah, because you have to have that time. By the time I got home, yeah, I would have told you straight to your face, I will never go back, ever. I mean, Robert Falcon Scott, in his journal before he died in Antarctica in a Scott tent, he wrote, "This is an awful place." Yeah, and having been out on the deep, I mean, McMurdo not included, but having been out on the deep ice after a couple of weeks, it's an awful place.
Yeah.
Thank you for joining us on Why Rocks, BYU Department of Geological Sciences podcast. We've been fortunate today to interview and discuss paleoclimatology with Dr. Landon Burgener, and we hope to see you again on our next podcast.
Bye.